Moments and the continuous uniform distribution. We've already seen a generator for a uniform distribution. We had a spinner, assumed to be frictionless. We spun it in zero gravity. It was recorded with the numbers from 0 up to 1. A weird stop determined a random variable x, a random number, in other words, in the interval between 0 and 1. We saw that every interval of length h had exactly the same probability, h, of capturing the value of x. So the cumulative distribution function, capital F of x, was 0 if x was negative, x, or the length of the interval from 0 up to x, if x is in the interval from 0 to 1, and 1 if x is greater than 1. This is called the uniform distribution on the interval from 0 up to 1. Corresponding probability density function. The probability density function you can get by taking the derivative of the cumulative distribution function, f prime of x. And that's equal to 1 provided x is strictly in the interval from 0 up to 1, and 0 elsewhere. You might have noticed that the derivative f prime of x doesn't exist when x is either 0 or 1. The function capital F is not differentiable there. And you might have noticed that I've more or less arbitrarily defined the density function f of x at those 2 points. The question is, does it matter how I define them at x equals 0 and x equals 1? Remember how we use a probability density function. We use it to obtain probabilities. We integrate it over an interval from a up to b to get the probability of that interval. So the question is, does it make a difference to those probabilities, to those integrals, if I define the density function arbitrarily at x equals 0 or x equals 1? The value of the function at 1 point, or 2 in this case, cannot affect integrals of the function. So for convenience, I've defined the probability density function to be 1 at x equals 0 and x equals 1. If I defined it to be something else, like 0, it would have no effect on probabilities and therefore represent the same distribution. Notice in the graph of the probability density function, it's essentially flat over the interval, and that's where the name uniform distribution comes from. We denote it, U for uniform, on the interval 0 to 1. And once again, the probability that x is between values little x and little y is f of y minus f of x, or y minus x, provided those values x and y are in the interval from 0 up to 1. The probability depends on the length of the interval. There is a more general uniform distribution that lives on the interval from a up to b, where a and b are arbitrary real numbers, a less than b. And again, it has the property that intervals of constant length within that interval ab all have the same probability, are all equally likely. For a random variable x that represents a random number between a and b with this property, we say it has the continuous uniform distribution, and write x tilde u ab. For a continuous uniform distribution, we know the probability density function must be constant. It must be flat at some value k, f of x equals k, over the interval from a up to b. What is the constant k? We can determine what it is by integrating the density and remembering that all probability density functions integrate to 1. So the integral from a to b of f of x equals 1, which gives k equals 1 over b minus a. Now we have an expression for the uniform AB probability density function. Little f of x is 1 over b minus a if x is in the interval, and 0 if x is outside the interval. Once again, we can define it arbitrarily when x is either a or b. The cumulative distribution function of a uniform AB distribution is, as always, obtained by integrating the probability density function. And in this case, this gives 0 for x less than a. It gives the integral from a up to x of 1 over b minus a if x is in the interval. And it gives us 1 if x is bigger than b. Well, the integral from a up to x of 1 over b minus a is x minus a over b minus a. I've graphed the cumulative distribution function here. It's flat and 0 up to the point A. It goes linearly then from A up to B, where it reaches its maximum value of 1, and then it's flat subsequently. How do we get expected values for continuous random variables? Suppose I have an arbitrary function g of x. G of x might be x or x squared or x cubed, and I'm interested in the expected value of g of x. If x were discrete, what would we do? We'd take the values of g of x, multiply them by the probability function, f of x, and add over all possible values of x. It's a sum over all x. And for continuous random variables, we do something that's highly analogous. The real question is, what do we mean by add? Where you used to take a sum over a discrete set of points, we now integrate. There are too many to sum. There are an uncountable number of points, and therefore we integrate. And so the expected value of g of x is the integral over all values of x, g of x, f of x, dx. And by all values of x, I mean x in the real line from minus infinity to infinity. So the integral minus infinity to infinity, g of x, f of x, dx. And of course, the single most important special case of this is the expected value of x, obtained by integrating x times the probability density function f of x over the whole real line. Similarly, e of x squared is obtained by integrating x squared times f of x. And for the variance of x, it's easiest to use the second expression we had for variance, e of x squared minus the quantity, the expected value of x, the whole thing squared, since we've just determined the value of these two immediately above. Example, mean and variance of the uniform AB distribution. Here's a plot of the uniform density function over the interval from a up to b. The height, the maximum height of the density is 1 over b minus a. The middle of the density, its center, is at the average of the 2 points a and b, namely a plus b over 2. Suppose I have a uniform distribution on the interval a up to b. Then the expected value of x is in fact that center point, a plus b over 2. It makes sense it should be the average of the values in the interval. The variance of x is b minus a squared over 12. And the median is identical to the expected value of x, namely a plus b over 2. The median, at least, is quite obvious, since it's clear from the picture that 1/2 of the area under the density function lies on either side of the point a plus b over 2. Let's check these moments for the uniform distribution. The expected value of x is the integral of x times f of x over the whole real line, but because f of x is only non-zero between a and b, that turns out to be the integral of x times 1 over b minus a. Or 1 over b minus a, x squared over 2, evaluated between the limits a and b. And this gives b squared minus a squared over 2 times the quantity b minus a. It simplifies, in fact, to b plus a over 2. What about the expected value of x squared? For that, we do the same integral, except this time the integral of x squared times f of x. And a similar calculation gives me b cubed minus a cubed over 3 times the quantity b minus a. You can check that for yourself. Finally, what's the variance of x? It's the expected value of x squared minus e of x, the quantity squared. B cubed minus a cubed over 3b minus a minus the quantity b plus a over 2 squared. And a little bit of algebra will show you that that's b minus a squared over 12. For the median, we've already argued for the median, but in general, we should solve the equation f of m equals 1/2 to find the median. The solution to that equation here is m equals a plus b over 2. So the expected value or the mean of a uniform 0-1 distribution is 1/2. The variance is 1/12. And in the computer language R, which you've seen in this class, the command for generating or simulating a vector of independent uniform random numbers is runif, R-U-N-I-F, bracket n. N describes how many values you'd like to produce. Review problem 1. Suppose a random variable x has a probability density function, 3x squared, on the interval from 0 up to 1. Elsewhere, f of x is 0. find the expected value of x and the variance of x. The expected value of x we've seen is the integral of x times f of x over from minus infinity to infinity, but we need only integrate from 0 up to 1. Elsewhere, f of x equals 0. And that becomes the integral of x times the density function, 3x squared, which is 3 times the integral of x cubed from 0 up to 1, which is 3/4. Again, the expected value of x squared is a similar integral, with x replaced by x squared, and we obtain, as a result, 3/5. And so, as before, the variance is the expected value of x squared minus e of x, the quantity squared, 3/4 minus 3/5 squared, which turns out to be something like 0.39. Comparison between discrete and continuous distributions. We've used the same kind of notation for discrete and continuous f of x. In the discrete case, f of x represents the probability function, but in the continuous, the probability density function. We've done that because the formula for things like probabilities and expected values are quite similar. For example, the probability x is in some set A or some interval. You get in the discrete case by adding over all values of x in A, f of x. And in the continuous case, by integrating the probability density function f of x over the set or interval A. What about the probability x is equal to a given value? In the discrete case, that's what we mean by the probability function f of x. In the continuous case, however, the probability of any one value is 0. The law of total probability says that when we add the probability of all values, we get 1. So in the discrete case, the sum over all values of x, f of x, is equal to 1. And in the continuous case, the integral from minus infinity to infinity of f of x is equal to 1. The cumulative distribution function, capital F of x. In the discrete case, we get this by adding the values of the probability function f of z for all z less than or equal to x. Analogously, in the continuous case, we integrate f of z from minus infinity up to x. The expected value of a function of g of x in the discrete case is the sum of the values of the function g of x times the probability of those values f of x. In the continuous case, it's a similar object, the integral of g of x times f of x. So, the expected value of x, the sum of x, f of x in the discrete case, the integral of f x times f of x in the continuous. E of x squared, the same idea, the sum of x squared times f of x, discrete, integral of x squared f of x, continuous. And in both cases, we can get the variance of a random variable x by taking e of x squared minus the quantity, the expected value of x, the quantity squared. Review problem 2. Suppose x has a probability density function f of x equals 2x on the interval from 0 up to 1. Everywhere else, f of x is equal to 0. Find the expected value of the function e to the power x. The expected value of e to the x we get by integrating the values of the function e to the x times the probability density function f of x over the interval of minus infinity up to infinity. But in this case, since the density function is only positive in the interval from 0 up to 1, we only need to integrate from 0 up to 1. And we can replace f of x by its formula in that case, 2 times x. If we take 2 outside and we integrate x e to the x dx, we end up with a value 2.